Okay, afternoon, everyone. Uh, the plan for just kind of a peek ahead on what's happening. Number one, the lectures will be done for in this week. Okay, so there'll be no new lecture material after this Wednesday. Monday is of course a holiday. Next Wednesday, we are going to spend some time part half. Actually, the TAs will be doing it with me joining it, kind of partly as a review, but partly also to go over the kind of design assignment we are handing out. So I decided to remember originally I had said there will be 3 design assignments. I decided to merge them. So merge second and third into one, and kind of just simplify things out there. So there are 4 topics essentially which we have not examined you meaningfully outside the PSET 2. So one is FSM, the other is data path plus FSM, third is this timing stuff that we are going through, and there's a 4th topic which we'll see on Wednesday or might start today. The quiz, which will take place next week on Friday, in lieu of the discussion sections, because kind of the 10th week, will consist of examining you primarily on FSMs, timing, and this next module, which is pipelining or improving thing. Okay, and final, which would be in the form of a design assignment, design plus an accompanying set of Q&A about the design. That I will hand out on Monday of the final week. It shouldn't take you more than kind of, let's say, a week, a day of work in terms of how you approach it. But I'll give you 5 days because different students have their other finals on different days, and that would be due end of the week, by Friday midnight, except for students who have approval from CAE, who can take. So no late days on that one, but CAE students will, if they have approval for timed things, they will get corresponding extensions on that. So that's what's going to be happening. So next, so this week discussion section is important because this is the one which is going to cover both the timing and it's kind of this week's material, and that's the last time you're going to see us. And then there is a review next Wednesday, which is kind of just 2 days prior to the quiz. So anyway, so that's what's going to be happening. If you have any questions, something, just reach out to me on Piazza and on this issue, and I'll make a posting there as well. So I'll skip logistic related Q&A here because I want to finish the material. Okay, so last time we began to see kind of a physical view of the circuits that we have been doing thus far, combinational, sequential, everything. And in fact, last time we saw kind of how combinational circuits, we can think in terms of these delays called contamination delay and propagation delay. And just to remind you what contamination and propagation delays were. Propagation delay is the time when the input last changes to the time output become last changes. Okay, so like let's imagine some action happens on the input bits, and then the output bits will change in response. And typically, for reasons I explained, some output bits may change before others, and also an output bit may go up and down before settling. So we are basically saying, and ditto on the input bit. So let's say a change happened on input bit. The last time it happens, that is after that, input bits are stable for now. So that's T3. And output B becomes stable at T4 from that point on. So it's the gap between T4 and T3, which is the propagation delay. Contamination delay is other way around. It's say earliest change on input to the earliest change on the output. Okay, and that's the contamination delay. And we kind of also talked about last time. I showed you examples on that. When you have circuits in series, then these 2 types of delays add up. So if I have 2 combinational circuits in series, then their contamination delays add up and their propagation delays add up. I'd also made the point last time that for primitive gates, like a 1 input AND gate, right? I mean, AND gate, which takes, let's say, 2 inputs of 1 bit each and has a 1 bit output. For something like this, the propagation delay and the contamination delay are one and the same. If circuits are in parallel, then things get more interesting because you have to consider all possible paths from an input pin to an output corresponding output pin. And the idea then is that contamination delay is the minimum across all the paths and propagation delay is the maximum across all the paths. And I kind of worked through a simple example, and then we had this kind of more complicated example. So that's where we were last time. And I had also made the point that don't confuse contamination delay with the minimum propagation delay or minimum delay. They're two very different concepts, and sometimes kind of people mix the two. So contamination delay is not the same as minimum delay. Contamination delay, in a way, is basically saying that if a change begins to happen on the input, and I was expecting output to remain stable for a while, but that may not be true. The output may start changing very quickly, even though it doesn't become stable until much later, right? So it's kind of like the jumpiness of the output. And we'll see why it matters very, very shortly, okay? So that's where we were last time. Now, all of this stuff was about combinational circuits, right? We're just talking about combinational circuits. Now, how does it affect sequential circuit? And that comes in the form of properties of flip-flops and sequential circuits more generally, called setup time and hold time. So we are going to talk about that. Yeah, go ahead.
So I just had a question. So like in the example where we had T1, T2, T3, and T4, like a few slides previous, would the minimum like delay time be T4 minus T1?
Don't even think about minimum delay time, okay? Just think in terms of contamination delay and propagation delay, okay? When people talk about minimum delay, what they typically talk about is minimum value that T4 minus T3 can take across temperature and different copies of the circuit. So it's a very different concept. So for a given circuit, there is no such thing as minimum delay.
Oh, okay.
So think about like this. T4 minus T3 may be affected by temperature. It may be affected by which copy of the chip you have. Let's say Intel makes two circuits. I get one, you get one. They're identical nominally, but my circuit may have a smaller value of T4 minus T3. So it's some manufacturing variation that happens. And the final thing is that the data value may affect. So let's say if A is 10, if there's a circuit where A takes some 4-bit number, and let's say A happens to be the number 8, then maybe the delay T4 minus T3, propagation delay T4 minus T3 is different if input A was 8 versus if input A was 6. So minimum would also say, what is T4 minus T3 across all possible inputs? Okay. So it's a very misleading concept. Don't worry about it. In context out here, it will only sort of confuse you. Okay, but that's what minimum means. Minimum across different conditions.
Okay, thank you.
Sure. So, so let's start with setup and hold time. So again, let's go back to our, as a figure I've seen shown before, like our sort of generic view of a sequential logic system is that there's a combinational logic block which computes the next state and which computes the output, and we have the state register which takes the next state, clocks it in at every clock tick, and outputs the state which we show out here, which is like the current state, right? So this is current state. Sometimes we call it current state, sometimes we call it previous state. So there's no standardization of jargon there. Okay. One thing to be very careful is that usually, so it's positive edge, but just remember, if I have a circuit like this, that means the active edge is downgoing one. Okay, so just remember that, because if you are not careful when looking at a circuit, then you may get it all wrong. Okay, so make sure you understand which tick upper the state register is changing at. Okay, so let's go back out here. So what is really happening is the following. Remember, I've often said that action happens at the clock tick, and in this case at the rising clock edge. So what's happening is that at the rising clock edge, the state register takes the next state and puts it into the register, right? And the output of the register, which is what we're calling a state, always is supposed to reflect what is happening, what is stored inside that register. So in an idealized view, right at the clock edge, next state will get put into the put into the register, and state will immediately reflect that. And in an idealized world, all of this thing will happen instantaneously, right? I mean, as when the clock edge comes, next state will get dumped into the register, and state will reflect this new value in the register. So if you look at the circuit below, what's happening is that at this first clock edge, we see that the next has a value, some value, which is SB. And kind of the idea is that currently, let's say we had SA out here. So initially, the current value in the register was SA. And so that's what is appearing on the wire. And the effect of that will go through, and currently input has a value A. So it is going through. And now we have, and if you call this thing a function f, right? So the next state function to be f, then here we are seeing f of A and SA, right? Some combination logic. So that's what you are seeing, that f of A, SA, okay? Now at the clock tick, this SB, which is f of A, SA, is what will get stored into the register. So this is what you see, that a little bit after the clock tick, the state changes to SB. And the same game will go every time. At every clock tick, you will see that a little bit after the clock tick, you will have potentially a new state occurring. Now, looking at this, and we already previously saw that how voltages don't change instantaneously, right? All of these things take time and all. So a couple of things stand to reason. Firstly, there is always some delay after the clock tick, right? The second thing is, for all of this thing to work, my input to the state register needs to be stable, right, before the clock tick, because clock tick is not like a instantaneous thing. It takes, if you're lucky, let's say some tens of picoseconds or something like that, right? But still takes some time. And if the input, which is input to the state register, namely next state, is changing at that time, then all hell can break loose. Right? So we have to make sure that whatever input we are trying to capture into the state register remains stable in this period, so for some time, right? And that will depend upon, we'll shortly see, on the flip-flop itself. So these two things matter. There is some requirement that it should remain stable, and actually not just remain stable until the clock edge, perhaps remain stable a little bit after the clock edge also. So two things follow, therefore. There is delay and there is stability requirements. And that's what we are going to be spending time on, and because they play a very, very crucial role. So let's zoom in. Let's zoom in on a clock edge for a D flip-flop. Okay, so now just think of that. I'm looking at one of the flip-flops in the sequential circuit, and it looks something like this, right? There is an input D, the clock tick comes, output is Q, and that's what we have. And at the clock edge, what is happening is that because the input D had a value X, then after some time, output Q will see the value X. And remember, we also talked about that before Q changes from its old value to new value, it may jump up and down, or may go through some, if it's a multi-bit value, then it may go through some intermediate values. So that's why you see this stuff out here, right? I mean, it may go through a zone of uncertainty. So with this, what is happening is, you can think of like the clock is sampling the input. At the time the clock edge comes, we sample the input D, and then we store it into the flip-flop, and then flip-flop's memory, and then it appears on the output of the flip-flop. So generally, the picture will look like this, and this leads to a few parameters that we have to worry about. One is, how much before the clock edge we want the input to remain stable, right? And that is TS. And let's see. Okay, so we require that for some time T sub S, the input D should have a stable value prior to the clock edge. Okay. So, and that is referred to as, we'll shortly see, is referred to as setup time. And then likewise, we also require that the input to the flip-flop remains stable for some time after the clock edge. So in effect, we are saying around the clock edge on either side, this input should remain stable. Okay, and this is what we call as T sub H, and that's called the hold time. Okay, so this is called setup, and I think we'll have on the slide later, and this is called hold. Okay, so we set the input up and we hold the input after that. Then what is happening is after the clock edge comes, the output to the flip-flop will begin to change and then stabilize after some time. So there are two things, right? How soon it begins to change and how late does it become stable. So the output may change as soon as TCCQ, that's what you see out there, and no later than TDCQ. So this is kind of a little bit like contamination and propagation is playing that role. How soon it can begin to change, and how in the worst case, how long would it take to remain stable? So to answer Jack's question, is TCCQ contamination? Yeah, it's playing that role out here, although contamination, strictly speaking, is for combinational logic, but it's playing a very similar role out here. Why is there both a high and a low for the inline? Why is it? Because if it is a multi-bit signal, then that's how we represent. Okay, so this is kind of representing general case. Okay, so 4 parameters, right? Setup, hold, what are TS, TH, TCCQ, and so TCCQ is saying what's the earliest time Q begins to change after the clock comes, and TDCQ means what's the latest time Q will change after the clock comes, provided the setup and hold times were met. Okay, so that's those are the 4 parameters. So TS again is setup, TH is hold, and you can think of this guy as kind of like contamination, and this guy is like propagation. One other thing to remember is that even though I'm kind of saying that this is for a D flip-flop, it's actually, these concepts are true for arbitrary things. So you can say true for an arbitrary sequential system, right? An arbitrary sequential system will have some input, multiple bits, right? D will have some output, multiple bits, let's call it Q, and it will have a clock. So these concepts that we are talking are not limited to D flip-flop. It's just that D flip-flop is probably the common component you will use, and therefore you will have these timing parameters available to you as part of a manufacturer's data sheet. Okay, whereas for a sequential system that which is more complex, you will have to derive these values. What is the setup for it? What's the hold for it? What is TDCQ? What is TCCQ? So they are not given. So that's the only difference. And for D flip-flop, it will be given to you generally as part of the whoever is providing you that. Whereas for anything else, you have to kind of figure it out. Okay, so now let's see what role they play. So very importantly, this thing affects both the performance and correctness of a FSM that you implement, a sequential system that you implement. So let's think about it. That let's say we have this where min and max represent combinational logic. Okay, and we are basically saying that the combinational logic. So these are CL. Both are combinational logic. Min means it has smaller delay, and max means it has bigger delay. Okay, it's the delay with the with a long propagation delay. Okay, and min has a short propagation delay. And let's see what role they play. So we have this is a system with 2 bits of state, right? Assume that we are given their setup and hold time and on. Okay. Now what will happen? So this is a logic path with the minimum delay. This is a logic path with the maximum delay. Now let's work out one requirement. So let's say a clock tick comes. We are going to look at what happens between 2 successive clock ticks. So let's say we are examining this clock tick. Let's call it clock tick 1, and let's call it this clock tick 2, right? At clock tick 1, it will, let's start at the upper D flip-flop. So the clock tick, after some time after clock tick, A will become stable, and that will take time TDCQ, right? It will take time, which is the propagation delay for that flip-flop. Then that signal A will propagate, right? I mean, A goes through this max, and then it will become available at the bottom flip-flop in our example. And TDCQ, so that's the signal B, right? So this signal A, after some time, will cause B to begin to change, and then B to become stable. So during this, so B will begin to change, but eventually B becomes stable. Okay, and then the next clock tick comes. So we need to make sure that when the next clock tick comes at the bottom flip-flop, B is stable for some time. And how much time does it need to be stable? Well, that's the setup time, right? So we want to make sure that this time out here exceeds the setup time. So what's going on? From the first clock edge, A will become stable after TDCQ, guaranteed, right? It won't, that's what the flip-flop spec says. Then from this point to TDAB later, so from A to B, whatever is the propagation delay, that is when B will become stable. And this instant out here must be such that I have enough time remaining before the next clock tick arrives, right? Because that for the second flip-flop at the next clock tick, I have to meet the setup time requirement. So what that gives us is the following: TDCQ plus TD max. TD max is what we are calling as TDAB, right? Because max is going from A to B. So TDCQ, which is the delay out here, plus TD max, which is the delay out here, plus the setup time of the second at the second flip-flop, all of that absolutely must happen in this time interval, right? And so it must be less than TCY. This is TCY. So we have to make sure that all the stuff on the right hand side fits into one clock period, because if it doesn't, then at the next clock tick, the bottom flip-flop may not function correctly. And of course, there may be some gap in it. It could be that TCY is 100, whereas the right-hand side is 90. That means I have 10 time units of slack in our margin in our system, right? So that is what is being shown out here, that in this particular case, there is a little bit of a slack also that is present. So you can say T slack is equal to TCY minus all of this term. Okay, so this is a very important condition, because if you fail to meet it, then there is no guarantees on the operation of the flip-flop. So in any sequential system, for every pair of flip-flop, what I mean by that is, for every flip-flop output to every flip-flop input, if you trace through the combination logic, this condition must be met, right? So in this example, there are only two paths which are going from a flip-flop output to a flip-flop input. So I'll have to consider this thing for AB one, and I'll also have to consider it for CD, except that I told you a priori that CD is a faster path. So I am only checking the slow path. So you can also say that this is really telling me how fast can my circuit operate, because let's say I find that my currently chosen TCY is less than the right-hand side, then all I can do is I can bump up the TCY. Bump up the TCY basically means I'm dialing down the frequency of the clock, right? So I can always slow down my circuit, slow down the clock frequency, and meet this requirement. Of course, I'm slowing it down, so I'm losing performance. But I could always do that, right? And in fact, let's say it turns out that the delay of your circuit depends upon something. Let's say it depends upon temperature. Then if you want to play a game like this, what you can do is, as the temperature goes up, then the combinational delays tend to go higher. So this is kind of generally, as the temperature goes up, gates get slower. So the right-hand side will become larger. And then what you do is you can respond to it by making TCY larger, in other words, slowing down the clock, which is why in modern computers, when things heat up, okay, and even your fan is unable to keep up, then the CPU will slow down. It is called thermal throttling, okay? Thermal throttling. And actually, you will see, those of you who are into games and all, you will see that your graphic cards, GPUs do the same thing. Okay, so that's what's going on. It's this equation under the hood that is responding to sort of how gates are responding to operating conditions. Okay, you may also have this issue that, like I said earlier, that you may make many copies of the same chip, but just because of manufacturing variations, some chips have faster gates and some chips have slower gates. And so what usually companies like Intel and all do is they basically pick and advertise a value of clock rate, which they know will work for most of the chips they are manufacturing for that model, for that part number, right? So let's say when they manufacture a chip, let's say the frequencies can range, let's say some Gaussian distribution around 1 gigahertz, let's say. So what they'll do is they'll say, okay, we want to pick some clock frequency. So I'm going to put the slowest clock frequency that will make sure that 99% of my parts work. For the 1% that they don't work, we will check it before shipping out. And even if we fail, worst come to worst, it's this cost of doing business, right? Now, this is where people who overclock their computers come into play, right? So if you're a gamer, you try to kind of run your computer as fast as possible. So now your particular computer, you may be lucky that is faster. So you can start boosting the frequency until it fails. And also you can cool the CPU down. So that's why there's a whole business of like coolers and all for your CPU chip, so that you can run it colder, which reduces the gate delay, which lets you then boost up the clock frequency. So there's all this game that you can play, but at the heart, this is what is going on. So now let's pause and look at the questions. Okay.
Can you clarify a bit what happens when thermal throttling occurs? Like what delays are lengthened and what?
Okay. Yeah, sure. So these two lengthen. Okay, so affected by temperature. Okay, so the delay goes up as temperature goes up. Okay, so now so if temperature goes up, then these delays are going up, and then either your system will stop working because you insist on keeping the clock frequency, or you respond by lowering the clock frequency. And actually, there is an interesting feedback loop out here, right? Because the power your system consumes depends upon clock frequency. If you run it faster, it dissipates more heat. So you can have a situation of thermal runaway. You increase the clock speed, and as a result, more heat is produced, which causes the gate delays. Well, it produces more heat, and if you don't respond to it, then kind of the delays keep going up. And actually, I also didn't mention, but there is actually, as temperature goes up, the gates also consume more and more power. So basically, more and more power for same operation. So you kind of end up into the situation that if you don't react in this thermal throttling very quickly, then the temperature inside the chip will just keep going up and up, and actually it can hit temperatures which are like really, really high. Like if you look at some of the papers, the temperature inside can hit like nuclear reactor type temperatures. Okay, so which is if you don't do anything, which is why cooling is done, okay, to keep that temperature under control. So thermal throttling is that in response to rising temperature, you react by reducing the power consumption of the system, and also react to it by reducing the clock frequency. The clock frequency is kind of your big control knob, right? As you lower it, power goes down, and you also prevent failure, this condition being violated. Okay, so in modern systems, it's very common that, unlike, like if you were to go back even a few years ago, like most systems had fixed clock frequencies. Now it's not doable. Okay, any of your phones and GPUs and all, they all basically mess around with the clock frequency using pretty smart algorithms, okay, to kind of predict what is happening. They try to model how the temperature will rise and then react to it. They also put sensors so that they sense what the right-hand side is for your particular chip at that moment in time, and then they set the clock rate accordingly. Okay, so, and some of the more modern, really cutting-edge stuff makes use of even fancy AI machine learning algorithms and all to do it. Okay, so there's a lot which goes on in this clock rate management. Okay, but underlying it is this equation and the thermal part. Okay, kind of two go hand in hand. Very roughly speaking, higher the clock rate, then you are doing more activity per unit time, and therefore you'll be moving more energy per unit time. In other words, you'll have more power consumption. So clock rate is proportional to clock frequency. Power consumption is proportional to clock frequency. And power dictates the thermal dissipation. So given if you're cooling the same amount of time, then as you're burning more power, but you're not able to remove it, right? Your removal rate is fixed, but you're producing more power. So all that heat is getting trapped, the temperature goes up. And as the temperature goes up, then the delays go up and power consumption goes up. And that's when you enter into this vicious cycle. So you react to it by bringing down the clock rate or improving the cooling system, which means turning on the fan speed. So if you have a PC and you go to the BIOS, you would see that you have all these control over the different fans that your system has. Okay, so all that, I guess, the heart of it is this issue. Okay, so this is, at least the good part out here is that I can deal with violations of setup time by slowing down the clock. Unfortunately, the next one, we are not so lucky. Okay, so next one is the following. Now imagine the following situation. First clock tick, what happened is I'm going to start at the bottom. So I'm now going to look at the fast path. Okay, things being too fast is not good also. Okay, so let's say a clock edge comes at the bottom thing. So what will happen is that as the clock tick comes out here, the output C can begin to change as soon as TCCQ after that, right? So from clock tick to C can begin to change as little as TCCQ after. So that's what you're seeing out here, okay? And then as C begins to change, then D will begin to change TCCD after, right? I mean, this is the TC min, that is the contamination delay of the upper combinational logic. So D can begin to change as soon as TCCQ plus TC min after the bottom clock edge. But remember, the upper flip-flop is also operating, right? And remember, it had a hold time requirement, right? It has to, that the input to the upper flip-flop should remain stable for some time after the clock tick. So I need to make sure that this moment doesn't happen before the hold time is up. So in other words, hold time must be less than the total contamination delay from clock edge coming to this bottom flip-flop to D changing. So this is saying that if my circuit is too fast, if contamination delays are too short, then I may end up violating the hold time of a following flip-flop. And so this equation must be satisfied. Now, right, so the previous one was about setup time. This one is about flip time. Now, if you look at this, there's no clock period in this, right? This is really about what's happening at a clock edge. The problem is you have already designed your chip, right? So TC-CQ and TC-min are whatever they are. You can't go back and redesign that chip that you just spent millions of dollars designing. And TH is also a characteristic of your silicon, right? It's the characteristic of the flip-flops in your design. So all of these parameters are fixed by design plus manufacturing.
What is TH and what is TC min?
TH is the hold time. Go back out here, right? This is the TH.
Mm-hmm.
It's the time for which the input to a flip-flop or a sequential system should remain stable after the clock edge. And TC min is basically the same thing as TC C2D. It's the contamination delay across this.
Okay, thanks.
Okay, so what is this is saying is that the contamination delay of the bottom flip-flop plus the contamination delay of min should be less than hold time for the upper flip-flop. By the way, the same requirement also holds true for the other path also. It should also be the case that TH is less than equal to TC-CQ for the upper flip-flop plus TC max. Except that since I already told you that the bottom circuit is slower, so TC max is larger than TC min. And so if the bottom equation is not satisfied, then the bottom equation is satisfied, then the upper equation is already satisfied. So I only need to worry about the quick paths in this one. In the preceding one, I had to worry about the slow paths. Here I have to worry about the fast paths. And we are basically saying if a path through my circuit is too quick, then it can lead to a hold time violation. And the challenge out here is that this equation is really, there's nothing under my control. Unlike the preceding one where I could slow down the clock, I can't do it out here. So I have to make sure at design time that my circuit, my chip once made, will meet this requirement. And if I fail to do it, then I'll have a dud chip because there's absolutely nothing I can do after once the design has been manufactured. So this one is a much more critical bug, right? A critical, like if you have a hold time violation in your design, then you better fix it at that time because your chip isn't going to work. Okay. So this one is kind of more important from an economics perspective. So if violated, this one we cannot fix by slowing the clock. There is nothing you can do once the chip has been manufactured to fix this issue. Okay, so the tools that are used to design chips, the simulators and all, they do a lot of testing to make sure there are no setup time and hold time constraint violations, but you should pay particular attention to hold time constraints because those can't be fixed later. Okay.
What exactly happens if this is violated?
Great question. So at that stage, you cannot guarantee that the flip-flop is getting into the correct value. And it's not simply that it may, like instead of 1, it may be a 0, or instead of a 0, it may be a 1. It may actually get into something called metastability failure. So if you're truly unlucky, then metastability failure can happen, in which case the flip-flop goes into a non-digital mode. It basically hangs into values which are illegal values for digital perspective. So if metastability failure happens, I mean, that's truly, truly bad. There's nothing you can do. You just repower up. Okay, so, and the thing is, actually, also one story that I'm not telling you is that all of these things, these delays, are kind of statistical in nature. So what I mean by that is there's always a probability that despite all your simulations and all, your circuits running circuit may violate these requirements. So there's always a tiny probability that this metastability failure or such things may happen. A metastability failure may happen in a circuit that you tested at design time. but people push it. Like if you get flip-flops, and you will see that if they are well documented, they will have a metastability failure rate, and the rate is typically like 1 in a trillion years or something like that, right? So effectively won't happen in any like statistically. You'll have to be like super unlucky for it to happen while your system is running. So they design these things that way, and there are flip-flops which are called metastability hardened, which truly take extra effort. So essentially, your goal with these things is, remember, not perfection, because you cannot achieve perfection, but really to make sure that the mean time to failure is very large. Could you please repeat the previous slide? Which one is the previous slide? This one? Right? Okay. So this slide is basically saying that if the delays are too large, then my computation may not be done before the next clock tick. That's basically what the slide is about, right? So at the first clock tick, some activity started happening, and we are looking at the slow path out here because that's what will matter. So let's say we start looking at clock 1, edge 1 coming at the upper flip-flop, right? I mean, edge 1 is coming at both, but we are looking at its effect on upper flip-flop. Then TDCQ, after that, A will become stable. Then TD max, after that, B will become stable, right? That's the worst case spec. So we are guaranteed that this much after the clock edge, B is stable. But B must become stable at least T sub S before the next clock edge. That is the requirement coming from the flip-flop. So this whole term must fit into a clock cycle, into one clock period, and therefore this right term must be less than the clock period. This is clock period, right? So it's basically saying finish all the computation, finish all the combinational delays, and leave margin for setup time within a clock cycle. So that's what this one is saying. And as I pointed out, we can always react to it by slowing down the clock. This one is saying that I have a shortcut in my circuit so that when I start computing as a result of a clock edge, when I start my combinational stuff as a result of clock edge, then some signal may change at some input to another flip-flop, or even my own flip-flop can change too quickly. And if it changes too quickly, then hold time will get violated. And so I need to make sure that my circuit is neither too slow nor too fast in a way, right? I mean, this contamination delay, my combinational logic should have sufficiently large contamination delays. So these two equations and the meaning of what they stand for is super important for you to understand. I can guarantee you that we'll have questions around this in the quiz. Okay, so do study it. So this one, if we violate, we cannot fix by slowing the clock. You can't really do all the three terms out here are fixed once you design and manufacture the chip. So there's nothing you can do about it. So let's say you designed something and you ran your design tool before shipping your design to the fab house, and it comes back and says, hey, there is a hold time violation happening between some pair of flip-flops. This equation is being violated. What would you do? So between some pair of flip-flops, the contamination delays are less, adding up to less than the hold time. Add gates, yeah. So we have to bump up the right-hand side, right? So we have to add some more, right? So there are a couple of options. Maybe I can slow down min even more by using a less efficient design. Like, let's say maybe it's turning out that the problem was occurring because I was smart and picked some fancy carry look ahead adder or something like that. Maybe I'll replace it with carry ripple adder or something. Let's use a slower design, right? So I could do that. or artificially add gates. Maybe if I'm running into problem, I can add some even number of inverters out here, right? I can slow things down to do it. It sounds easy. It's a little bit tricky. Firstly, when you're adding gates, you still have to make sure that all of this will keep working at all temperatures. Remember, this equation has to hold true across all temperatures that your chip will face. And usually for commercial designs, I mean, you aim for, let's see, if you're unlucky enough to be living in very cold places, your temperature could be like minus 40 degrees Celsius, Fahrenheit, whatever, right? And if, and the same product also has to work in, I don't know, if you're unlucky to live in Death Valley, then temperatures are whatever, 130, 140 Fahrenheit. You can reach up to there. So you're looking at a truly large range of temperatures over which even commercial products work. Now imagine you are NASA or US military, and the ranges you see for those products are even more so, right? And then we have people who put stuff, electronics down volcanoes and stuff like that, right? I mean, or sensors which are inside machinery or nuclear reactors and things like that, right? Even more. So when we say that this equation and the preceding equations hold, right, these two, what we are really saying is under all operating conditions that you envision your product to be working at, and that makes things super important. But going back out here, what's the solution? Yes, Jack's solution, we add gates. Does this happen often or just in some rare cases? Happens often. Yeah. So and both of these issues, right? I mean, what is your initial design may not meet it, and so you'll work at it. Now, having said that, if you are using some of the modern design tools, then when they synthesize the circuit, right, from your Verilog thing and all, they try to make sure that these constraints are met. That is, they will not give you design options which clearly violate these requirements. But if on the other hand, you have some manually designed pieces and all, then you can easily run into these troubles. Yeah. Okay, so let's pick up some examples up here. Okay. So let's say I have the same circuit, except I tell you, so it's the same circuit as well, right? Let's say I tell you TDCQ and TCCQ, the propagation delay and contamination delay in the flip-flop, as well as the setup time. They're all 150 picosecond. Hold time is 250 picosecond. TD max, which is the propagation delay through the max combination logic block, is 850 picosecond. And TC min, which is the contamination delay through the upper combination logic block, is 100 picosecond. So first question, is hold time constraint met? So to check whether the hold time constraint is met, I need to make sure that if I go through this path, then right, because min is the faster one, min has a lower contamination delay, that I'm not running into problem. So what is the, from clock edge to C is 150. Then from C to D is 100. So that's 250. And my hold time was 250, right? So the two are just match. Hold time is equal to my total contamination delay. So is the hold time constraint met? Yes, although just barely. You don't have any margin. So you better make sure that your design is not, that these, you have picked worst case numbers out here. What is the minimum cycle time? Okay, so minimum cycle time, I have to look at the long delay, right? So I'm going to start, since I kind of upright told you that the bottom combinational logic block is the slower one, so we're going to focus on that. So from getting from clock to A is TDCQ, which is 150, plus delay through max, which is 850, plus setup time, which is 150. So we end up with 1150 picosecond. So inverse of that will give you the clock frequency, but this is the minimum clock cycle time, right? If your clock cycle time is slower than that, then you will have a violation of setup time. So so that's how it will work. Let's look at another one. So firstly, is this clear? Any questions on this one? So
Can you further explain the minimum cycle time when you were unclear on how you picked the values for that?
Okay, so 150 is this guy. So let me pick a different color. So this would be the TDCQ. Okay, and let me play the same game out here. This is 4. Okay, but try not to get into a pattern matching mode, because it's very easy for me to offer you questions where pattern matching approach will fail. So let's again try to understand why the issue is happening, right? In first case, with the hold time here, the issue that we are worried about is that a change started by a clock edge, its effect propagates too quickly, so that at some flip-flops input, a signal is changing too quickly after the current clock edge. I'm considering a clock edge, and I am supposed to keep the signal stable for some hold time, and I'm not meeting it because I'm too quick to change, right? And the second one is really worried about the case where at one clock edge, some action started at a flip-flop, and I have to make sure that all the resulting action from it is done before the next clock edge, right? And we are worried about that there exists some path from one flip-flop to another a flip-flop output to a flip-flop input where this condition is being violated. So try to make sure that you're convinced the reasons behind these two equations, okay? And not simply look at the algebraic form. Very important. Okay. Let's try this one out. Consider a D flip-flop with, do I have answers to these? Yeah, right. So consider a D flip-flop with TS equal to 50 picosecond, TH is 40 picosecond, so setup is 50, hold time is 40. So which means that for this D flip-flop, input must be stable for 50 picosecond before and stable for 40 picosecond after the clock edge. TCCQ and TDCQ are 60 picosecond. So from the clock edge to the output of the flip-flop changing is 60 picosecond. And we are using a bunch of these D flip-flops to implement state register. The next state logic has a propagation delay of 800 picosecond and a contamination delay of 50 picosecond. Compute the setup and hold time slack. So margin, right? Slack is how much margin do I have in my design when I operating at 1 gigahertz, right? So first thing to remember, clock cycle has no role to play in the hold time case, right? The hold time constraint is purely a characteristic of the circuit, whereas the setup time constraint is also involves a frequency. So let's look at it. So the slack in setup time, right? So we are basically saying how much slack is available in the setup time. So so we can basically, what we are basically doing is going back to our equation, right? We are basically saying how much smaller the right-hand side is to the left-hand side, right? That's the slack, because that means that I can bump up the gate delays by that amount and I'll still be okay, right? My right-hand side can grow a little bit more. So that's what's happening out here. We look at the clock period minus, and these terms were my right-hand side in the original equation, right? So clock period is a time I have available. During that time, I have to fit in the delay through the flip-flop, delay through my next state logic, and the setup time. So TDCQ is the flip-flop delay, which is 60, right? TD is the propagation delay through the combinational logic, the next state logic, right, which is 800, and setup time currently is 50. So it's 50, we subtract 90 picosecond. That means I can use a flip-flop whose setup time is 140 and I'll still be okay. Or I can use a next state logic whose propagation delay is 890 picosecond, I will still be okay. Or I can have a flip-flop whose clock to output delay, CQ delay, is 150 picosecond and still be okay, right? I mean, I can basically cause these terms, the three subtracted terms, to kind of go up a bit, and I will still meet my requirements. So that's the margin, okay, that we have. And I can do the same thing for hold time. So for hold time, it is, remember, the issue is that after the clock tick, I don't want things to change too quickly, right? So I want to make sure that the contamination delays through my flip-flop and combination logic are larger than the hold time. So that is why you see this thing, right? This is, these two terms constitute the delay through flip-flop plus combination logic, and set hold time is the characteristic of the flip-flop. So TCCQ is 60, TC is 50, and TH is 40. You subtract it out, 70 picosecond. It's basically saying I have a safety margin of 70 picosecond. If I got my estimates wrong and the contamination delay and flip-flop delays were smaller, I'll still be okay as long as that margin is still met. So usually when you are designing these systems, you're going to leave these margins, because it's very hard to estimate. Like, I mean, I'm writing these things as, setup time is 50 picosecond and all. These are just estimates coming from some modeling of the design and simulations, right? I mean, they themselves have margin of errors. So you always try to keep some safety margin in your design, so that even in the face of uncertainties that you didn't account for, your design would still continue to work. So the TAs will go over some more examples of this nature, but again, I will really strongly urge not to look at the names of the variables and the precise algebraic form of the equations, because we may change the names of the variable, right? I mean, we may not follow the same symbolism. Like out here, I simply wrote that next state logic has propagation delay of TD, okay, instead of some TD AB or something like that. So don't get thrown off by those. What really matters is the concept, which is what that we are trying to accomplish, that setup time is about meeting a deadline. That is, action started at one clock tick should complete before the next clock tick. And hold times are about not being too quick, because if you are too quick, then other people, other flip-flops who are currently doing their work, they may fail. Okay, so you don't want to be too quick. Don't leave your colleagues behind, so to say, right? I mean, make sure that they also finish the job at the current clock edge. And the flip side is that, and make sure that finish the job before the next clock tick arrives. So that's what's going on out here. Any question on this example? Okay, so skew between clock. So a confounder in this whole story is, remember, in all of these things, we were kind of assuming that the clock tick reaches the two flip-flops at the same time, right? Like when we were reasoning about it, these things, we kind of assumed that magically this clock edge, like if I was sitting and as an external observer and looking at these flip-flops, then we kind of have this assumption that by my watch, when the clock tick occurs at the bottom flip-flop is also when the clock tick occurs at the upper flip-flop. And that assumption is not true, because clocks travel over wires. Wires have capacitance. Imagine a chip where clock is sitting in one, clock enters the chip at one part, right? So this is what I'm trying to say, right? Let's say there is a flip-flop here. And let's say there is a flip-flop here. And let's say my wire look like this. Now, how long can this chip be? Well, nowadays, big chips could be around a couple of centimeters, let's say 3 centimeters, worst case, or maybe a couple of centimeters. And this is within the chip. Same story holds true at the level of the whole board. Well, what is speed of light? Speed of light is 3 × 10⁸ meters per second, or 3 × 10⁻10 centimeter per second, right? Which is another way of saying is that it is 0.3 centimeter per nanosecond. Sorry, did I get right? So speed of light, c, is 3 times 10 to the power 8 meter per second equal to 3 10 to the power 10 centimeter per second. So 3 centimeter per 0.1 nanosecond. Okay, which means that it takes around 0.1 nanosecond for clock to travel from here to there, right? So you can, and now imagine you may have like hundreds of thousands of flip-flops all over the chip. So clearly there can be a spread. I mean, the clock edge may be reaching them at different times, and that spread can be of this order, right? A few tenths of a nanosecond. So and remember, we operate our modern chips at gigahertz frequencies, right? I mean, so multiple gigahertz, like let's say your clock cycle is, let's say 5 gigahertz at the very high end chips, right? So that's like 0.2 nanosecond. So that means the skew, right? The differential between when the flip-flop, bottom flip-flop and the top flip-flop are seeing the clock edge is already like half your clock period. That's huge, right? So our assumption that clock tick reached the flip-flops at the same time is really very risky. So clock skew deals with that issue. Skew refers to that the clock may reach one flip-flop a little bit after it reaches another flip-flop. Okay, so and if you have a design with hundreds of thousands, they may just reach different flip-flops at different times. So that's what we have tried to show out here, that it's the same circuit as we had before, except we have modeled the skew as this. So this is the skew. We are basically saying that on the path from the clock source to the upper flip-flop, there is some delay. So the clock on the upper one reaches TK after it reaches the bottom one. And you can think of TK to be a signed number. So if the bottom one sees the clock later, then TK is just negative, right? I mean, it's relative is all that matters out here. Okay, so what implications does it have for our design? So in this particular case, the upper one is seeing the clock tick TK after the bottom one sees the clock tick. And we were, so now let's think about both our cases, right? I mean, so we were worried about the setup time and the hold time. So let's look at the setup time. Setup time, we worry about the long path. So we worry about this path, right? So in this case, what will happen is some work started happening at the clock tick, goes through the contamination delay here, goes through, this one is setup time. So goes through propagation delay here, goes through propagation delay here, but the clock edge out here, let's say my clock period was 100 nanoseconds. And let's say the clock edge came here at t. The next clock edge here will come at t plus 100. But the clock edge here came earlier, right? It came at t minus tk. So the next clock edge will come here at t minus tk plus 100. So the gap between my clock edge and the next clock edge here, clock edge at the bottom and the next clock edge clock edge at the top and the next clock edge at the bottom is actually less than my clock period because the skew is working against me. So what is happening is then this TK term appears out here. So not only do I have to meet my propagation delay and setup time, but I also have to worry about skew. So if I'm unlucky, then skew can eat into my margin. So, and that is happening because the clock tick came a little bit later at the flip-flop, which is the starting point of my long path, right? So I already ate into my budget there. And it's the same story which will hurt us with hold time. So in the hold time, we are worried about this path, right? That's the short path. So TCCQ plus TC min. But now what is happening is that, remember, in hold time, we worry about the current clock edge only. But the current clock edge comes later at the top flip-flop. So it's already eating into some of my budget. So we have a minus TK term out here. So in this example, TK is hurting us for both the dimensions, right? On the other hand, if bottom flip-flop saw the clock later, right? If TK was negative, then I'm better off, right? If TK is negative, then this term will become positive, and then my expression is easier to meet. And if TK was negative, then this term would contribute negatively, and then again, I can generate a faster clock. So skews play a very important role, and depending upon which flip-flop is ahead versus behind can have a huge role to play. And this kind of suggests another thing, which is one way to cope with hold time issues is to manipulate your skews, wire things differently so that the clock signal reaches the flip-flops at a time in the order you choose. So let's say, for example, if I have flip-flops lined up in an array like this, and if my clock was like this, signal travels here and then meets here and then meets here, that will have a very different effect than if I were to generate my clock this way, right? Very different in terms of skew. And one may help you, and one of these choices will help you, and the other may hurt you. Okay, so one can examine the way you lay out the wires on your silicon can also have a huge impact out here. So any question? This is a little bit of a tricky concept. So the skew. So what I'll do is the following. Let's take a it's 707 or something like that. Sorry, 507. So let's start at 5:13. So take a 5-minute break. Think over it, and we'll discuss it more. But grasping skew and why it is helping or hurting is super important. Okay, so let's take a short break. Think of questions that you want to ask me, and so 5 minutes. We'll start. Okay, let's resume. So I'm going to walk over this slide again. Okay, so the challenge that we are facing out here is, and now I'm going to refer to the timing diagram here. Okay, that the clocks are reaching at different times at the two flip-flops. So the bottom flip-flop sees the clock CLK as it is, but the upper flip-flop is seeing the clock after a bit of a delay, and let's call it clock D. So this is as seen by upper flip-flop, right? So the clock has been shifted as seen, and the impact. So now let's reason about how it is affecting the hold time. So in hold time, we are worried about the green path, the faster path. So after CLK comes at the bottom flip-flop, TCCQ after that, C begins to change. And TCCD after that, D begins to change. So D begins to change at this time. And hold time is relative hold time for the upper flip-flop starts from when it sees the clock edge, and it is seeing this clock edge. So the hold time is out here. Versus, imagine if there was no skew, then the hold time would have started relative to this guy, right? Because if there was no additional delay for the clock to reach, and that would have been better for us, right? I mean, because what we are trying to do is we want to make sure that D doesn't begin to change before hold time is up. So if TK goes up, then I'm more at risk of violating the hold time. And that is what you are seeing in this equation, that if TK goes up, then right-hand side goes down. And for a given hold time, I will potentially reach a violation, right? I mean, if TK is too large, then minus TK would subtract away a lot of my margin, and I will run into a violation out here. And the same story holds true on the downgoing edge, right? I mean, if I look at the next clock tick, then the next clock tick will come at bottom flip-flop before the next clock tick comes at the upper flip-flop. And there I'm worried about the red zone. So there, again, the skew eats into my my budget and hurts me. And you see that in the form of TK appearing out here. So if TK is large, my right-hand side goes up, and so I'm at the risk of violating this particular constraint. Let's see, do I have an example? Okay, so yeah, so we are going to look at an example, but before I kind of move on, just want to ask any questions on this. Could you explain again how we got TK, how we get a negative TK? Oh, so the way you get a negative TK is, for example, as I shown out here, let's say I was routing my design so that the clock came from the left. Just by physics, the signal traveling, it will reach flip-flop 1 before it will do flip-flop 2. So in that case, it means that flip-flop 1 will see an earlier clock edge and flip-flop 2 will see a later clock edge. But let's say I reverse the direction of the signal. I put my clock source on the right-hand side. Now flip-flop 2 will see it first because the clock signal will travel this way. So I can, and then reach 1. So by appropriately positioning how I wire up, right? I mean, if you start from the clock source and those flip-flops which are closer to you along the wire will see the clock edge first, and those are later will see the clock edge later. So I have some degree of control by which at the wiring time, right? And this actually suggests a way to combat hold time things, right? I mean, if I'm running into hold time violations, so besides what Jack had suggested that we can add gates, I can also play with how I lay out on silicon where the flip-flops are and how they are receiving the clocks. I can play with the play with the skews to again solve this problem. Okay, so negative, now in our particular case, let's imagine that the clock at the bottom flip-flop came later. That is mathematically equivalent to saying that TK is negative, right? I mean, so if TK is positive, then upper flip-flop gets the clock later. If TK is negative, then bottom flip-flop gets the clock later. Okay, so to Aiden's question, think of it as it's a vector quantity. I mean, in physics, we learn about direction, right? So all that matters out here is which direction, who is later. So if A comes after B, that's the same as saying A comes before B with a negative time value. There's mathematically no distinction. Okay. So imagine if instead of this circuit, I had wire out here and I had a delay out here, right, with a TK. You work it out. I mean, this is exactly the way you'll do it in physics, right? I mean, if X comes after Y by 10 seconds, that's the same thing as saying Y comes after X with minus 10 seconds later. Okay. So it's not that there are negative delays, it's how I'm mathematically modeling it. I'm modeling it as a vector, as something with as a signed quantity. And you try to work it out. I would urge you to work out the case where bottom flip-flop gets the clock later and see what you are going to get. Any other questions? Okay, so let's work out this example. So this is the same example we had before, except now we have a skew of 75 picosecond, right? So we had seen this example before, just to recall your memory. It was this example where we had worked out how much slack I had on the setup time and the hold time. And we are going to see that our skew sort of hurts the slack. Okay, so our slack is 75 picosecond. So what will happen in this case? For the setup time, it will eat away into the slack, right? I mean, into this. So instead of previously 90, I will have 90 minus 75, 15. And what about the hold time? Previously in hold time, I had, go back out here, 70 picosecond. Now again, it will hurt, and it's -5. One thing to remember is that when you have faced with these kind of problems, assume clock has a skew of 75 picosecond and we're asking something, you have to consider the worst case for you, right? So don't consider the beneficial direction of skew, but the adversarial or whatever, the hurtful direction of the skew. So we are going to assume in this case that my skew is such that it is hurting me. And so what you see out here is that if there is a skew of 75 picosecond, the setup time still has margin left, so I'm okay. But hold time is now -5 picosecond, a hold time constraint. That means I have a violation. So this is bad, right? So what it's saying is my design, if for whatever reason faces this kind of a clock skew, then I'm in for trouble. So that's a violation. Let's look at another example. Okay, so this is with respect to our same diagrams which we have been using, this kind of stuff. Okay, so we are given TDCQ, TCCQ, TS. So all of this is about my D flip-flop. Okay, we are given a hold time, TD max, TC min, TK. Okay, so now we have a skew of 100 picosecond. Is hold time constraint met? And is minimum cycle time met? So recall, what did my cycle time well, let's look at the whole time. So the whole time was that the 2 TCCQ plus TC min, that is 850 plus 100. And I wanted TH, which is 250, to be less than equal to this, right? I mean, if we go back just to refresh your memory, TH looks like this. Except what happens is now that I have skew, so skew eats away out here. So sorry, not this. 100 plus 150, 250, right? So it was previously meeting it correctly. And now I have a minus TK. So I eat away minus 100. So this becomes 150. And so I have a violation. So skew, I was very evenly matched, but now there is a violation. Let me ask you the following. What is the minimum cycle time? So why don't one of you attempt this one, or whatever, all of you attempt and tell me, what do you think? So just to refresh your memory, originally my cycle time was, let's go back. Where did I have? Yeah, we had it 1150, right? We had said that it is 150 because of the flip-flop delay, 850 because of the TD max, and then another 150 because of the setup time, and all of that added up to 1150. My question is, what do you think is the minimum cycle time now if I have a skew? Yeah, 1250. Excellent. So hurts us, right? So it slows down the clock. Okay, let's look at this one. Firstly, so I'm giving you an FSM. Look at it and tell me what does it do. Anyone? Yeah. So it is multiplying. So Max is absolutely right on. It's basically taking the current state and adding to it the current state shifted left by 1, which is the same as current state by multiplied by 2. So it's basically doing current state plus current state times 2, which is 3 times the current state. So at every clock tick, it's multiplying the state by 3. Okay. Now, assume for this full adder has a contamination time of 10 and propagation delay of 30 picosecond. So minimum TC, minimum contamination delay between flip-flops is 10 picosecond, right? Because I could go like this, flip-flop go like this, right? So that could be 10. And the maximum between flip-flop can go through all of these things, right? So it can start out here, go like this, 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 come like that, right? So it can go through all the 16 flip-flops, and that one will correspond to the max. 16 times 30, 480. So my worst case delay from some flip-flops output to some flip-flops input is 480. That's the worst case. So that's a propagation delay. And the contamination delay, the quickest delay, is something at any bit, and that's 10. Assume for D flip-flop, we are given 10 picosecond contamination, 20 picosecond propagation, setup of 20, hold time of 10. Question: is the setup requirement met? Oh, okay, Zaid's question. Let me answer that. Do you agree that X next is S plus S left shifted by 1, which is the same as S plus 2 times S, which is the same as 3 times S? Okay, 1, 1 is 3. It's not 11, it's 3. Boolean 3.
Where did we shift by 1?
Look at the wiring out here, right? We are shifting here, right? So at every bit, the second input of the full adder is coming from the preceding bit, right?
Oh,
right, like this bit here is feeding here and is feeding to the one out here.
Okay, thank you.
Okay, so back to this. So what is the hold time constraint being met? So remember, hold time constraint was TH should be less than equal to the flip-flops contamination delay, which is 10, right? Plus the combinational logics contamination delay, which is 10. And TH is equal to 10. So TH is less than the contamination delay, so we're okay. So that's what it shows. What is the minimum cycle time? I guess my animation didn't work out right. So you see the answer out here. So here we are worried about the propagation delays. So propagation delay through the flip-flop is 20. So that's this guy. Combination logic is this guy. And then this guy is the setup time, which is we have out here. Okay. And all of that adds up to 520. So minimum clock cycle that we can sustain is 520 picosecond. So let's see. Can a skew of 20 picosecond be tolerated? So let's look at it. Here we were, if I get a skew, then the right hand side will be affected, and I'm telling a skew of 20. So right hand side was already 20. If 20 disappears, we'll be left with 0. So hold time cannot be met, right? So it will be violated. So answer is no, right? So skew, what is the maximum skew I can tolerate? Well, the maximum skew I can tolerate is 10, right? Because right hand side would then become 10 plus 10 minus 10, which is 10, which meets the left hand side, right? So maximum skew tolerable equals to 10. Okay, so it can't be tolerated at 20. So what can we do? What can we do? Anyone? Faced with this circuit, redesign D flip-flop, right? I can redesign the D flip-flop to have a hold time which is better, right? I mean, now unfortunately, that's not really going to help. If I have 20 picosecond, then I will need a hold time of 0 picosecond. So is the maximum skew tolerable equal to the slack? Yeah, it's the slack on the hold time, absolutely. Reduce clock skew. Okay, so I can do that. These, neither one of these are practical though, just bear that in mind, right? I mean, the flip-flop is whatever it is. So you have to catch these problems at design time, right? I mean, once you ship it out to TSMC or whatever to fabricate your chip, it's too late. You have just already spent millions of dollars. So add logic with 10 picosecond contamination delay before each D flip-flop. So you could do that. So anyway, so those are some of the measures you can take. Okay. So to summarize, delays in digital system, you basically have to worry about delays to the combinational one, which is propagation and contamination, right? Combinational and in the flip-flop from clock to output. But for flip-flop, even more important are these startup and hold times. And we have these two equations, right, which you really, really absolutely must try to understand. Like I said, you will have questions on this in quiz. Right, so one is hold time and the other is setup time related, right? Setup time related, I can always deal with by slowing down the clock. That may not be desirable, but at least your circuit will work, right? I mean, at some clock speed. So, clock skew affects both. If you have control over the clock skew, the way you are wiring, maybe you can even use it to your advantage. But generally speaking, you have to be prepared that clock skew can hurt you, because so what happens is we design our hardware, right, and in these high level tools and all, right? I mean, and then we get a schematic, and then we use some other set of tools to place the parts on silicon and wire them up. So there is it's kind of like a top down design flow. So at the time you are designing the circuit and selecting parts and all, you'll have to make some assumptions about what will be the clock skew, because it's very costly to wire this to come up with this with the circuit like components and how they're connected, then do the placement and routing on silicon, and then realize something and visit back. Just put in perspective, each run through your tools may take days, right? So it's not something I run it, oh, oops, it violates hold time, let me cycle back, right? I mean, you're looking at chips which are huge, and moreover, these are chips being designed, like, I mean, if you look at a typical Intel microprocessor and all, right? I mean, it's being designed by multiple teams and spread across countries, and also iteration is very different ball game than just like a small piece of code which you just iterate over. It just doesn't work like that. So you run into lots and lots of issues. So you have to so typically when complex digital systems are designed upfront, you kind of budget for these things, and everyone has to honor their part of the design and make sure that you are meeting these things, because if you discover these problems when the hardware is being integrated, it's already too late. I mean, of course, if it's fabricated, then it's super bad. Okay. I still have no idea how you got the minimum clock cycle time. Which slide are you talking about? So minimum clock cycle time, is really an outcome of this equation, right? If it is saying clock cycle time has to be greater than the right-hand side, then the right-hand side is the minimum clock cycle time, right? Does that make sense, Nathan? Okay, so back out here. So I think it was Aiden who had asked, what happens if we violate setup and hold time, right? So let's say you did all your stuff and all, and luck wasn't with you, and some flip-flop when your chip is running did violate. So I had mentioned at the time that the thing goes into a non-digital mode. So this is an oscilloscope. This is a photo of output of a flip-flop which has gone into this mode. So it is called, when you violate these things, then you may begin to see the output of the flip-flop go into these weird analog oscillations and all. Okay, so this is called metastability failure. Okay, you notice out here, so this whole thing is metastability. And if you are lucky, if you wait long enough, it will come out of metastability failure, but possibly not sufficiently in time for you. And if you are unlucky, it can linger there for a long time. Okay, so I just wanted to show that bad things happen, and there's a whole field. A lot of this stuff goes into the umbrella of reliability of these systems, right? And so there are people who study it, and they study these kind of failures and things like that, and how you make circuits which are hardened. Now, a challenge with setup and hold time is the following. Thus far, we were talking about these kind of diagrams where the flip-flops were receiving signals from other parts of your own circuit. But remember, your chips have to interact with the outside world. So at some place, there will be signals whose timing you don't have any control over, because they are being driven by human beings or external systems. So a challenge is, how do you make sure that your setup and hold times are met when your signals are coming from sources over which you have no control? So fundamentally, therefore, it is impossible to prevent setup and hold time violations from happening, right? Unless your system is sitting in an isolated universe where everything is under your control, which is no practical system will be like that, right? So it's inevitable that your design will get signals from outside, and therefore it's inevitable that you have a chance that they will run into violation of setup and hold time. So what your best hope is to limit such violations at the boundary of your circuit. Okay, and so people create these special flip-flops which are designed to have very good setup and hold time characteristics and all, and try to catch things there so that the main part of your system is not affected. So just want to mention that. It's a topic which is way too advanced for me to even attempt. I don't do that kind of work, so in any case I can't say something terribly meaningful, but those of you who end up taking some advanced courses will probably encounter it. Okay, so let's see. So now we move to the last topic in the course. So making systems faster. So let's say you did, thus far what I've described is, okay, you designed this circuit and you got the minimum clock cycle time, okay? And now your circuit works at that speed and it gives you some performance. But let's say you're unhappy with it. How do you deal with it, right? And this is where your role as a architect comes into play. Remember, you have control over two things. You have control over the algorithm behind your design, right? Some of you encountered it already in the design assignment, but you have control over the design of the circuit. Sometimes the two have to come together. And there are very broadly kind of two techniques that you can do to solve this. One is do things in parallel, and the other is do things in a pipeline, like an assembly line, like a car assembly line. We are going to examine the latter and how it helps us. And you will see that these things, if done right, it can help you in speeding up the overall performance of your system. So this is chapter 23 of the book. Okay, and it's one of the more advanced topics. But let's start with the following. So let's say I have to do some tasks, A, B, C, D. So let's say I have to finish a total job, I need to do A, B, C, D. So conceptually, there are two ways I could do this kind of stuff, right? And depending upon how it's possible. So maybe it's possible that I can chop A, B, C, D are independent of each other, right? I mean, so it's kind of like, let's say I want to add 5 groups of, or 4 groups of, four pairs of, like I have pairs of numbers and I have to add each pair within each pair, and I have 4 such pairs. So I could have a single processor do first pair, then second pair, then third pair, then fourth pair, or I can have 4 processors, one handling each pair, right? So the okay, so bottom one reflects that, and that we can have in parallel. So I think the example in this figure is meant to be like parallel lanes on a road, right? I mean, and then the other one is when there is a sequence of things to happen, like to do a job, A needs to be done, then B needs to be done, then C needs to be done, and then D needs to be done. So one way I can do it is I have one process, one hardware, which does A, B, C, D. Once it's done, then it goes and picks the next job. But in pipelining, what I can do is, let's say, so again, I have a sequence of jobs arriving. So while D is doing, so let's say I'm getting job 1, job 2, job 3, like that. So J1 comes here, A does it, then A handles it to B. So J1 goes here and A starts doing J2. Then J1 goes to C, J2 goes to B, and J3 arrives out here. And then finally, J1 goes out here, J2 goes out here, J3 goes out here, and this guy starts doing J4. So that's how car assembly pipelines or oil flow pipelines work, right? I mean, the newer entrant enters the pipeline while the initial entrant has moved along, right? So conceptually, this is how there are kind of 2 ways you can do things more quickly, right? Jobs more quickly. So pipeline is like an assembly line, right? I mean, we see all these photos of like car factories and all, or right? I mean, things are, the workers, the robots, they are stationary, and the product moves from one station to another station, right? So the computing task moves from one hardware to the next hardware to the next hardware, and each one of them does the next bit on it, right? In a sequence. So pipeline is like that. So let's say, and in some senses, we have encountered a little bit of this in the full add when we did the ripple carry full adder, right? And I'd complained that, it takes, like if I order of n delay, right? If I have n bits, then the delay is proportional to n. Now, what is happening in this ripple carry adder, right? Every stage adds the bits and the carry coming from the preceding side. So if you look under the hood, right, the carry was rippling through, right? So the lower bit did its job first, handed over the carry to the next bit. It did its job, handed to the carry to the next bit. So carry was rippling like this, right? But if you had the ability to examine the signals at the low level, you would see that activity happened here first, then here, and then finally out there, right? I mean, that's the rippling part. Now, how can I speed it up? Let's say because remember, right now it was a single combinational logic, kind of the whole thing. How can I speed it up? Well, what I could do is I can divvy it up into sort of 4 groups of 8-bit adders. So my original adder is 32-bit. So I'm just going to walk you through a design, okay? So I'm going to cluster together groups of 8 bits. So it will look like this, right? I mean, you can think of it as this is adding 8-bit, it produces the carry. Then the next group is adding another 8-bit, but it needs the carry from the preceding, and so on and so forth, right? And each one of these groups of 8 is really a 8-bit triple carry adder, okay? So thus far, all I've done is I've kind of just redrawn it, right? Groups of 8. Now we're going to think of these 4 groups as our pipeline, right? Some work happens in the lowest group. It hands the result, which is the carry out, to the next guy, and so on and so forth. So let's see how we can make it work. Now, how does pipeline happen, right? I mean, so think of like, actually, I don't know if you've ever been to a factory. These products move on the assembly line in a rhythm. Okay, so what happens is every worker would have some amount of time that they can spend, right? And every worker will have to spend equal amount of time, because otherwise the slowest worker will become the bottleneck. So the idea would be, let's say we will fix some time period. We'll say 5 minutes, let's say. And every 5 minutes, the product will move to the next station. So every station has 5 minutes to do its job. So when the product arrives, 5 minutes, you do its job so that it can move to the next one, which is why, like when we read about like the time pressure that workers on Amazon warehouse and all are under, because they're operating in a pipeline, right? If you slow down, then the whole pipeline has to stop, and that affects the productivity of the whole factory, right? Or whole warehouse in case of Amazon. So what is our analog? It's the clock tick. Think of the clock tick is when the work moves, when the product, the data, right, moves from one combinational hardware to the next combinational hardware, where the next computation will be done. So clock tick is registers. So this is how our circuit is going to look like. This is what is called as the pipeline circuit. So what's happening is these are all registers, as you can see, right? So this is clock. And these are 32-bit registers. So what happens is my data enters from the left, right? So let's say it's present there. This group adds the lowest 2 bits, and it produces the sum, and it produces the carry. We do nothing on the data in the upper bits. At the clock tick, all of that, right? The data out here, as well as this carry and the sum, moves into this first register. And the next set of values will appear out here, right? So the outside world is also operating in the same clock tick. So at any, and then the job which we had started, in the next clock tick, in stage 2, we will add the middle term, and then stage 3. So this is like a pipeline. And at the clock tick, we shift the product so that whatever was the work, if you call these things as station 1, 2, 3, 4, then station 1 moves to 2, 2 moves to 3, 3 2 moves to 4, and 1 gets a new job. Okay. And meanwhile, we are carrying the results like this out here. So after 4 clock ticks, right? First, second, third, 4. After 4 clock ticks, our results will appear out here. Okay. It's exactly like a factory line. So let's look at an animation. Okay. Yeah. Do I have an animation? Yeah. I thought I had. Yeah. Okay. I have. So we started out with some values, right? So at the initial stage, and these values got worked upon, so we get these, whereas these are just the original data. Okay. So after the first clock tick, this is how it will look like, right? The sum and carry are sitting out here, and we still have some unprocessed data under P0. Next clock tick, things move there. Now my sum and carry have increased, right? I have sum for more bits, and I have carry out from the second stage. But now the new job which was being done, right? I mean, when we were out here, this stage was doing the next job. Its results are stored here. and then the third stage and the fourth stage, and now the whole sum is available, right? So after the fourth clock tick, the whole thing is available. Now let's think about this design, right? I mean, so firstly, hopefully you agree that this is mimicking the whole pipeline, and at any given time, I have actually, I think my animation messed up out here. I'm sorry. P012, yeah. This is P3, and this is S3. Okay. So at any given time, I have like 4 jobs in the system, right? Which are being worked out. So in this example, at this moment, these guys are doing P4, right? The 4th job. So one job is being output, and there are 4 jobs in progress. Okay. So that's how this kind of system works. And you can kind of also see that if you look at from a timing perspective, P0, task number 0, will start in 0th clock cycle and finish at the end of 3. Task number 1 will start in the next clock cycle and finish a clock cycle later, and so on and so forth. So what do we observe in this? We observe that one new job, one new task here is addition of 2 numbers, right? Addition of 2, one new task every clock cycle, right? And that's one. And the second thing is we are doing 4 tasks at any time at different stages. Now why do we go through all of this trouble? So let's go back out here. Our original design was this. Let's say my full adder had a delay of 10 nanoseconds. Then with this design, as we have, I'll present the input and I'll wait for the output, and the output can take so let's say full adder was 10 nanosecond, then it would take 32 times 10, 320 nanosecond, right? So my clock tick would have been 320 nanosecond. What do you think is the clock tick here in this design? How much work am I having to do between at any given clock tick? No, I think you seem to be on the right track. It's 8 time sense, right? We have 4 groups of 8 bits. So at any given clock stage, I mean, this is an 8-bit adder, right? This is each one of these are 8-bit adders. So it would be 80 nanosecond, right? Did everyone get it, right? I mean, so in the purely combinational design, I have to wait for 320 nanosecond before I can do the next addition. Whereas in this one, every 80 nanosecond, I can do a new addition. Now, the thing to remember though is any given addition would still take 4 times 80 nanosecond in our example, 320 nanosecond, right? So from start to finish, it's still 320 nanosecond. It's just that I'm able to initiate a new one every clock tick. So I'm able to do a new addition every 80 nanosecond, even though any given addition takes 320 nanosecond. Is this clear to everyone, right? I mean, that's what's happening with pipelining, right? That I'm initiating a new one every clock tick. Every clock tick is 80 nanosecond. So a new job every clock tick, but I'm taking multiple clock ticks to do a job, as opposed to a purely combinational one where I have to account for the whole job in that one clock tick. Any questions on this? Let me pause out here. Oftentimes this pipelining concept is not clear to people. So just want to make sure. Okay, so sounds like no questions. Everyone's getting it. So again, latency, which is start to end delay, that's unaffected. That's still 320. But I'm able to do more jobs. What is the cost? What did I pay for this? Like, is it all coming for free? More frequent clock cycles, but that is an artifact that I'm running. Nathan says more frequent clock cycles. That's true, but then that's what I wanted, right? I mean, I want a faster system. I want to do more things, right? So what? So now, one way I could have done is I could have taken 4 ripple carry adders, right, and do 4 jobs in parallel. Each one will take 320, but I will have 4 such things, so I'll have to pay 4 32-bit adders. Here, I have 4 8-bit adders, so essentially 1 32-bit adder, but I have to put these pipeline registers. That's the cost, right? These things are called pipeline registers, right? Let me write. So we are paying for that, right? I mean, I'm adding these registers out here. So, and by the way, these registers will have their own delays, right? So my clock period will not exactly be 80 nanosecond. It would be 80 nanosecond plus the setup time and those kind of things associated with these registers, but still close enough. So that's the pipelining concept. Now let's walk through this thing. Let's say each full adder had a delay, each 1-bit full adder had a delay of 100 picosecond. So before pipelining, the delay of our 32-bit adder was 3.2 nanoseconds. So this adder can do one problem every 3.2 nanosecond, or you can say it has a throughput. That's what we call it in computing. Throughput is the rate at which I can do work. So I can do throughput of 1 over 3200 picosecond, which is roughly 312 mega operations. That is, I can do 312 million additions per second. That's with my original design. Let's say we do the pipelining. So if we do the pipelining, suppose TDCQ, which is the flip-flop characteristic register, is 50 picosecond. Let's say TK, the skew is 50 picosecond. So I will have a 200 picosecond of overhead. Then what would happen? So in this example, each stage, right, each of the pipeline stage is doing 8-bit addition. So that's 800. And I have to also pay for setup time and skew. So it's 800 plus 200. So my clock cycle, instead of being 800, it's going to be a little bit higher. It's going to be 800 plus 200. And I need four clocks to do a job. So I will need 4,000 picosecond to do a job. Previously, I was doing a job in 3,200 picosecond. But I'm doing 4 jobs. So previously, I was doing 1 job every 3,200 picosecond. Now I am doing a job every 1,000 picosecond, or 4 jobs every 4,000 picosecond. So I can achieve a throughput rate of 1 giga operation per second, whereas previously it was 312 mega op per second. So I got a gain roughly of factor of 3 speed up. Right? So I'm not getting factor of 4, which is what ideally I would have. And the reason we are not getting is because of these overheads, right? This part. Because I put those pipeline registers, they are eating some of my clock budget. So my clocks, instead of being 4 times faster, are somewhat less than 4 times faster. But overall, I still come out ahead, right? I mean, essentially with some increase in area, right? You have to add those registers. I'm able to get factor of 3 improvement in the flip-flop, in the overall speed up. This trick is used quite a bit. Oh, I just realized that I way exceeded the time. So I'm going to stop out here. Apologies. I'm going to repeat this stuff next time. But pipelining is how we speed computation up. It's one of the 2 major techniques. So I'm going to pick this thread up on Wednesday, and we'll wrap up. I probably will not even need all of the lecture time on Wednesday. But anyway, sorry about this. questions. So even though it takes more time, it does more stuff. Each clock tick takes more time, but my clock ticks are a lot faster still than before, right? I mean, instead of previously they were 3,200, now they are 1,000, right? So my clock ticks are still faster. So it takes more time, but I am doing more work per unit time. So we'll discuss this next time. And again, apologies for not realizing the time. So, okay. So see you guys on Wednesday.